NASA has photographed the surface of Pluto. We've captured images of black holes 55 million light-years away. The James Webb Space Telescope can see galaxies that formed just 300 million years after the Big Bang. But there's something much closer. Something that completely surrounds our solar system, that remains utterly invisible. The Oort Cloud is a shell of trillions of icy objects that marks the true boundary of our cosmic neighborhood. Yet we've never seen a single one in its natural habitat. Even stranger, when scientists tried to calculate how invisible these objects should be, the math revealed something disturbing. The Oort Cloud isn't just hard to see. It's almost as if it's hiding. What NASA discovered isn't a limitation of technology, but a fundamental property of the universe itself that makes the most important region of our solar system completely undetectable. And the reason why has implications far beyond astronomy. Dr. Jennifer Walsh stood in front of a screen displaying what should have been impossible: empty space where something had to exist. It was 2019, and she was leading a team at the Southwest Research Institute attempting to directly image objects in the inner Oort Cloud using data from the Hubble Space Telescope. The strategy was elegant: use Hubble's exquisite sensitivity to search for faint reflected sunlight from the largest Oort Cloud objects, bodies potentially the size of Pluto or larger, drifting in the outer reaches of the solar system. The team had identified a promising target region based on gravitational perturbations detected in the orbits of several long-period comets. Something massive had disturbed these comets, sending them on trajectories toward the inner solar system. By working backward through orbital mechanics, Dr. Walsh's team calculated where that disturbing object should be right now: a specific patch of sky in the constellation Taurus, approximately 3,000 astronomical units from the Sun. Hubble pointed its cameras at that precise location and exposed for hours, gathering every photon of light from that region of space. When the images were processed, they showed exactly what every other attempt to photograph the Oort Cloud had shown: nothing, just the faint glow of distant background galaxies. Whatever had disturbed those comets, an object massive enough to gravitationally influence bodies millions of miles away, was completely invisible. "I expected it to be faint," Dr. Walsh later said in a departmental seminar. "I expected it to be difficult, but I didn't expect it to be absent. We were looking at a region where something with significant mass had to exist, and we saw nothing at all." The Oort Cloud's invisibility isn't a simple problem with a simple solution. It's the result of multiple factors converging to create what scientists call the perfect darkness, a combination of distance, temperature, composition, and geometry that renders these objects essentially undetectable by conventional means. Start with distance. The inner edge of the Oort Cloud begins around 2,000 AU from the Sun. For comparison, Neptune, the most distant planet, orbits at just 30 AU. Pluto, which took extraordinary effort to discover and photograph, sits at about 40 AU. The Oort Cloud is 50 times farther than Pluto, and that factor of 50 makes an astronomical difference, literally. The intensity of sunlight follows an inverse square law. An object at twice the distance receives 1/4 the light. At 50 times Pluto's distance, Oort Cloud objects receive 2,500 times less sunlight. They exist in near total darkness, illuminated only by the faint glow of a sun that appears as nothing more than a bright star in their sky. But dim illumination is just the beginning of the problem. Dr. Michael Zhang, a specialist in planetary photometry at UC Santa Cruz, explains what happens to the tiny amount of light that does reach these distant objects. Even if sunlight reaches an Oort Cloud object, most of it isn't reflected back toward us. These bodies are covered in dark organic compounds, carbon-based molecules that have been irradiated by cosmic rays for billions of years. This irradiation creates a layer of nearly black material on the surface. It's like trying to see a lump of coal in a dark room lit by a single candle a mile away. Laboratory experiments have simulated what happens to ice when it's exposed to cosmic radiation in the cold vacuum of space. Within just a few million years, the surface develops a crust of complex organic molecules called tholins. These compounds are extremely dark, absorbing more than 95% of visible light. Some experimental samples are so black they rival vantablack, one of the darkest materials ever created. This means Oort Cloud objects aren't just faint because they're far away. They're also naturally camouflaged, coated in material that absorbs nearly all the light that reaches them. The small fraction that does reflect is spread across such a vast distance that by the time it reaches Earth, it's indistinguishable from background noise. Dr. Zhang ran calculations to determine how large an object would need to be detectable by our best telescopes. The answer was sobering. Even with Hubble's sensitivity, an Oort Cloud object would need to be at least 400 kilometers in diameter, larger than most asteroids, to produce a signal strong enough to detect at 2,000 U, and that assumes the object has a relatively bright surface, which, as the Tholin research showed, they almost certainly don't. We could have a planet the size of Earth sitting in the inner Oort Cloud, Dr. Zhang said, and we wouldn't see it. Not with current technology. Not even close. But the invisibility problem gets worse. Even if an object were large enough and bright enough to theoretically detect, there's the problem of knowing where to look. The Oort Cloud is a three-dimensional shell surrounding the entire solar system. It occupies a volume of space so vast that the entire observable universe's worth of telescopes couldn't survey it comprehensively. Dr. Sarah Kim, an astronomer at the Harvard-Smithsonian Center for Astrophysics, put the search problem in perspective. Imagine trying to find a specific grain of sand scattered somewhere within a sphere the size of a city. You have a magnifying glass, and you can examine 1 square inch at a time. That's the scale of what we're attempting. The Oort Cloud covers essentially the entire sky from our perspective, and we can only observe tiny fractions of it at a time. Even dedicated sky surveys like Pan-STARRS and the Zwicky Transient Facility, which scan large portions of the sky nightly, aren't sensitive enough to detect Oort Cloud objects. They're designed to find moving objects in the inner solar system, asteroids and comets that are much closer and brighter. An Oort Cloud object, moving slowly against the background stars at such extreme distance, would be invisible to these surveys. Then there's the problem of motion, or rather, the lack of it. One of the primary ways astronomers find faint objects is by detecting their movement. By comparing images of the same region of sky taken hours or days apart, moving objects stand out against the stationary background of stars. This technique discovered Pluto, Neptune, and countless asteroids. But Oort Cloud objects move extraordinarily slowly as seen from Earth. At 2,000 AU, an object orbiting the Sun takes thousands of years to complete one orbit. From our perspective, it barely appears to move at all, perhaps a fraction of an arcsecond per year. This glacial motion makes it nearly impossible to distinguish from background stars using traditional methods. Dr. Kim's team attempted to overcome this by using multi-year baselines, comparing images of the same sky regions taken years apart. But even this approach failed. We found plenty of moving objects, she explained, but they were all either nearby asteroids or distant galaxies with high proper motion. Nothing matched the expected characteristics of an Oort Cloud object. The James Webb Space Telescope, humanity's most powerful infrared observatory, offered new hope. Unlike visible light telescopes, Webb sees in infrared wavelengths, detecting heat rather than reflected light. Even cold objects radiate infrared energy, and scientists hoped this might make Oort Cloud objects visible. Dr. Rachel Torres led an early Webb program specifically designed to search for these objects. The strategy was to point Webb at regions of sky where long-period comets had originated, looking for the thermal signature of the parent population still residing in the Oort Cloud. We were looking for objects at temperatures around 40 to 50 Kelvin, Dr. Torres explained. That's incredibly cold, only about 40 degrees above absolute zero. But even at those temperatures, objects should emit faint infrared radiation that Webb could theoretically detect. The observations were conducted in late 2023. When the data came back, the results were puzzling. Webb detected thousands of background galaxies, each glowing in infrared light from their own heat and starlight. But in the foreground, where the Oort Cloud objects should be, there was nothing above the noise threshold. Dr. Torres ran the numbers again, checking her assumptions. According to theoretical models, the Oort Cloud should contain at least several hundred objects larger than 100 kilometers in Webb's field of view. At 40 Kelvin, they should be detectable. Yet Webb saw nothing. Either the Oort Cloud is far less populated than we think, Dr. Torres said in a 2024 conference presentation, or these objects are colder than our models predict. And if they're colder, we need to ask why. This possibility opened a new mystery. The predicted temperature of Oort Cloud objects comes from basic thermodynamics. They should be in equilibrium with the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space at a temperature of 2.7 Kelvin. Objects in the Oort Cloud receive virtually no heat from the sun, so they should equilibrate with this background temperature plus a small amount of internal heat from radioactive decay. But what if something was actively cooling them below equilibrium? Or what if their surfaces had properties that made them radiate heat more efficiently than expected, dropping their temperatures below detection thresholds? Dr. Nathan Silva, a thermal physicist at MIT, proposed a disturbing explanation. If Oort Cloud objects are coated in highly porous, low-density material, think of it like cosmic aerogel, they could have extremely low thermal inertia. They would cool rapidly and maintain temperatures significantly below what we predict. They would be thermally invisible, barely distinguishable from the background temperature of space itself. Laboratory experiments with analog materials supported this idea. When scientists created icy samples coated with porous organic layers and subjected them to space-like conditions, the samples cooled to temperatures several degrees below equilibrium. Applied to Oort Cloud scales, this effect could render objects effectively invisible even to infrared detection. But the mystery deepened when Dr. Walsh's team made an unexpected discovery. While analyzing the orbits of long-period comets, they noticed a statistical anomaly. Comets arriving from certain directions in space were slightly more common than from others. The difference was small, only about 15% above the expected random distribution, but it was statistically significant. Random distributions don't have preferred directions, Dr. Walsh explained. If the Oort Cloud is a uniform sphere surrounding the Sun, comets should arrive from all directions equally. But they don't. There's a slight bias toward comets coming from the direction of the constellation Orion. When the team modeled what could cause this bias, they found only one explanation that fit. There had to be a region of higher density in the Oort Cloud in that direction. Something had concentrated objects there, creating an asymmetry in the otherwise spherical shell. But what could create such an asymmetry? Stellar encounters, close passes by other stars, can disturb the Oort cloud, but they typically strip away objects rather than concentrating them. Galactic tides, the gravitational influence of the Milky Way's disk, can create some asymmetry, but not in the direction observed. The concentration we're seeing, Dr. Walsh said, suggests that something massive has been gravitationally shepherding objects into this region, not stripping them away, but gathering them. And whatever that something is, it's either still there or passed through relatively recently in cosmic terms. The implications were unsettling. If a massive object, a rogue planet, a brown dwarf, or something else, had passed through the Oort cloud within the last few million years, it would have left exactly this kind of signature. But such an object would also be invisible by all the same mechanisms that hide the rest of the Oort cloud. It could be out there right now, drifting silently through our solar system's outer shell, and we would have no way to see it. Dr. Silva proposed a detection method that didn't rely on light at all: gravitational microlensing. This technique uses the fact that massive objects bend spacetime, acting as gravitational lenses that can magnify the light of background stars. If an Oort cloud object passed in front of a distant star, it would cause a brief brightening as its gravity focused the star's light. The problem, Dr. Silva admitted, is that we'd need to be extraordinarily lucky. The alignment has to be nearly perfect, and the event only lasts for hours or days, depending on the object's size and speed. We'd need to be monitoring millions of stars continuously to have a reasonable chance of catching one of these events. Nevertheless, some surveys have begun doing exactly this. The Optical Gravitational Lensing Experiment, OGL, and others monitor millions of stars in the Milky Way's bulge, looking for microlensing events. While their primary targets are exoplanets and stellar mass black holes, they could theoretically detect large Oort cloud objects. In 2022, OGL detected an unusual microlensing event. A background star briefly brightened, then returned to normal over a period of 18 hours. The duration and light curve suggested the lensing object was between 1 and 10 Earth masses and located somewhere in the outer solar system. Could it be an Oort cloud object? Dr. Silva wondered. Possibly. The mass and distance fit, but we only caught one event, and it's impossible to confirm. The object, whatever it was, has moved on. We'll never see it again. This single ambiguous detection highlighted the fundamental problem. The Oort cloud exists in a regime where our detection methods are barely adequate. We catch glimpses, hints, and shadows, but never the objects themselves. Dr. Kim proposed an alternative approach. Instead of trying to see individual objects, look for their collective effect. If the Oort cloud contains trillions of objects, their combined gravity should produce measurable effects on spacecraft trajectories, the orbits of distant comets, and even the paths of interstellar objects passing through the solar system. Her team analyzed the trajectory of Oumuamua, the first confirmed interstellar object, as it passed through the solar system in 2017. Oumuamua's path was slightly deflected by the sun's gravity, but there were tiny residual deviations that couldn't be explained by known solar system bodies. These deviations are minuscule, Dr. Kim said, only a few meters over the course of months, but they're real, and they suggest Oumuamua was influenced by gravitational sources we can't directly see. The Oort cloud is the most likely candidate. If confirmed, this would represent the first indirect detection of the Oort cloud's gravitational influence, proof of its existence not through seeing its objects, but through measuring how they pull on other things. But even this approach has limitations. The gravitational effects are so small that they're easily masked by other uncertainties: outgassing from the object itself, pressure from solar radiation, even the tiny thrust produced by thermal emissions. Isolating the Oort cloud's contribution requires extraordinary precision and assumptions that may not be valid. As technology improves, some scientists hold hope that new instruments might finally pierce the Oort cloud's veil. The proposed Habitable Exoplanet Observatory, HABEX, and LUVOIR space telescopes, if built, would have sensitivity far exceeding Hubble or even Webb. They might be able to detect reflected light from the largest Oort cloud objects. But Dr. Zhang is skeptical. Even with these next-generation telescopes, we're only talking about detecting the very largest objects, things the size of Pluto or bigger. The vast majority of the Oort cloud would remain invisible, and we'd still have the problem of knowing where to point. The search space is just too large. Dr. Walsh has become convinced that the only way to truly see the Oort cloud is to go there. We need a fleet of probes, she argues, hundreds or thousands of small spacecraft equipped with cameras and spectrometers, launched in all directions. As they pass through the Oort cloud, over decades or centuries, they'd image objects directly, map the cloud's structure, and finally remove this blind spot from our knowledge. The technology exists. Small, lightweight probes powered by solar sails or advanced ion drives could reach the inner Oort cloud within a human lifetime. The challenge is cost and coordination. Launching such a fleet would require international cooperation and funding on a scale never attempted for a purely scientific mission. Until then, the Oort cloud remains what it has always been: the solar system's invisible shell, known through inference and mathematics, but never seen. We've mapped the surfaces of distant moons, photographed exoplanets orbiting other stars, and imaged the supermassive black hole at the center of our galaxy. Yet the boundary of our own solar system, the trillions of objects that mark where the sun's gravitational dominance ends, remains hidden from view. It's humbling, Dr. Torres reflected. We pride ourselves on our ability to see across the universe, to detect the faintest signals from the edge of observable space. But something that surrounds us, something that's part of our own cosmic address, is completely invisible. It reminds us that there are still fundamental limits to what we can observe, and some mysteries might require us to physically go there to solve them. The Oort cloud isn't just hiding. It's revealing a profound truth about the universe. Darkness is the default state of existence. Light, visibility, and observation are rare and fragile phenomena. Most of the universe exists in shadow, and the fact that we can see anything at all is the exception, not the rule. Somewhere in that darkness, trillions of objects drift in silence, relics of the solar system's birth, captured interstellar wanderers, and perhaps things we haven't imagined. They've been there for billions of years, will be there for billions more, and for now, they remain the greatest mystery in our cosmic neighborhood. A mystery we know exists, but cannot see. Thanks for watching another episode. While you're still here, make sure to click the video on your screen for more quality content.